Today we will understand Riesz representation theorem. Every bounded linear functional f on a Hilbert space H can be represented in terms of inner product, that is fx is equal to inner product of x and z, where z depends on the value of f and f is uniquely determined such that norm of f is equal to norm of z. Now let's start the proof. First we have to show that the existence of z such that a linear functional f can be represented as inner product of x and z. Then we will show that z depends on f and is uniquely determined by f. And then at the last we have to show that norm of f is equal to norm of z. Let us start the proof. If f is equal to 0, then z should be equal to 0, as if we put z equal to 0 here, then it can be written in the product of 1 into 0, that is norm of x comma 1 into 0, and 0 can be taken out from here, then it will become 0 into norm of inner product of x comma 1, that will become 0. So here if f is equal to 0 then equal to 0, the result holds. Now we will talk about if f is not equal to 0. Since f is a bounded linear functional f, then there exists null space of f, that is n of f is a closed subspace of H. Then if we take f is not equal to 0, if f is not equal to 0, then null space of f cannot be equal to H. To show that null space of f is not equal to H, let us consider that null space of f is equal to H. Then we get that for all value of x from H, fx is equal to 0 for all x belongs to H. This means that fx is equal to 0 for all value of x. This shows that f is equal to 0. But here we get contradiction that f is not equal to 0. This implies that null space of f cannot be equal to H. Now, null space of f orthogonal is not equal to 0 by projection theorem. Now let us consider an element z0 not equal to 0 belongs to nf perpendicular. That is, z0 is orthogonal to null space of f. We have taken this, z is not equal to 0. Now for an arbitrary x belongs to f, let us consider a new element v. We have defined this element like that. V is equal to f of z0 minus f of z0 into x. Now we know by the property of f is a bounded linear function, so we can apply f here. Then f should be applied also on the RHS. Then f of this quantity. F is a bounded linear functional, so it can be separated out. So it can be written as fx into f of z minus f of z into f of x. That is this. And these values are same, so we can cancel out that is equal to 0. This shows that v belongs to null space of f. As f of v is equal to 0, then we can say that v belongs to null space of f. And we have taken an element z0 that is perpendicular to n of f. So inner product of v and z0 should be equal to 0. Two elements are orthogonal, their inner product is 0, we know that. V inner product of v and z0 is equal to 0. So we have put the value of v here, that is this, and comma z0 is equal to 0. So by the property of inner product space, we can write like this: f of x should be taken out and z0 comma z0, and if we take another combination of their, minus f of z0 should be taken out and x of z0 is written in the inner product, that should be equal to 0. So we know that inner product of shape quantity is equal to norm square. So f of x into norm z0 square is equal to f of z0 into x comma z0. So we can take this quantity and divide. So fx is equal to f of z0 upon norm of z0 whole square into inner product of x and z0. This quantity should be taken inside here, and we know that the inner product is sesquilinear and inner product is conjugate linear with the second argument. So this will become here, if we put there conjugate, so fx is equal to inner product of x comma f of z0 upon norm z square whole conjugate into z0. So if we take a whole quantity as z, we have shown that for fx there exists z such that fx can be written as inner product of x and z. Now x was arbitrary element we have taken from H. So for all x belongs to X, there exists z belongs to H that can be written in the inner product of x and z. Now it remains to prove that z is unique and norm of f is equal to norm of z. First we will show that z is unique and norm of f is equal to norm of z at the last. For uniqueness, let us suppose that x belongs to H. Then by the definition we have fx is equal to inner product of x and z. So we have taken two numbers z1 and z2. Fx is equal to inner product of x comma z1 is equal to x comma z2. At the last we will show that z1 equal to z2. This will prove the uniqueness of z. So if these quantities are equal, we can take it in LHS. Then we can write by the property of inner product. Space inner product of x comma z1 minus z2 is equal to 0. If we expand it, then it will become this quantity. So we can write like this. If we put x is equal to z1 minus z2 itself, in particular choose x is equal to z1 minus z2 belongs to H. We have put it x is equal to z1 minus z2. So this will become the norm square, that is norm of z1 minus z2 whole square is equal to 0. We know that norm of a quantity is equal to 0 if and only if that quantity should itself equal to 0. So z1 minus z2 is equal to 0, then z1 equal to z2. This proves that uniqueness of z, as we have taken fx is equal to inner product of x comma z1 is equal to x comma z2, and at the last we have proved that z1 equal to z2. This shows that z is unique. And the last thing we have to prove that norm of z is equal to norm of f. If f is equal to 0, then z equal to 0. Result will hold norm of 0 equal to norm of 0. Now we have to show that norm of z equal to norm of f for f is not equal to 0. F is not equal to 0, z is not equal to 0. Now fx can be written as inner product of x and z. We have proved earlier for x belongs to H. Then we can take mod in both sides, taking modulus mod of fx is equal to mod of inner product of x and z, and we know that the Schwarz inequality, it can be written like this: Schwarz inequality norm of inner product of x and z modulus is more than equal to norm of x into norm of z. This is due to the Schwarz inequality, so we can take it in denominator. Now norm of fx upon norm of x is more than equal to norm of z. Now taking supremum over all x belongs to H such that x is not equal to 0. The supremum x belongs to H, x is not equal to 0. This whole quantity is the definition of the norm of f. This should be known to us. The norm of f is equal to supremum of x belongs to H, x is not equal to 0, mod of fx upon norm of x. This is the norm of f. So norm of f is more than equal to norm of z. Now we will show that norm of z is more than norm of f. Then by both the inequalities we will say that norm of f is equal to norm of z. For showing that norm of z is more than norm of f, we will start as follows. Now since f is a bounded linear functional f, by the property of f is bounded, we can write mod of fx is more than norm of f into norm of x. This is due to the boundedness of f. We have known that. Then we can write like this. This should be taken here. Norm of f is greater than equal to norm of fx upon norm of x, and we know that fx is equal to norm of inner product of x comma z. We have proved this here. Fx is equal to inner product of x and z. So we will put here fx here, inner product of x and z. Now we can put x is equal to z. This will become norm of f is greater than equal to mod of inner product of z comma z upon norm of x. Inner product of z comma z is equal to norm of z whole square. This will cancel this. This implies that norm of f is greater than equal to norm of z. From these equals equation 1 and equation 2, we will show that we will get norm of s is equal to norm of z. Here the whole theorem is proved. This theorem is necessary very in functional analysis and is always asked in the paper at least 8 to 10 marks. That should be important for an MSc student. Riesz representation theorem, and the statement also is asked, so you have to learn the statement.